Welcome back. This is lecture 8.1, where we are going to talk about CV and the Equipartition Theorem. Okay, so this is a continuation of last lecture where we talked about CV, right? So this was the capital one, right? Which was partial Q, partial T at constant V, which we ended up being able to say that CV was also partial U, partial T at constant V, and we defined CP, which was partial Q, partial T at constant P, which we had to define to make this into an exact differential. To write it in terms of an exact differential, we had to develop the ideas of enthalpy. Okay, so last time I gave some examples for CP, right? And I did some liquids and solids and gases. But even though I gave you CP is a little bit strange to think about for a gas, right? Because when you think about it, the solids and liquids often, they retain their volume, right? Sorry, they can change a little bit in volume, but we often do things at constant pressure. That is usually atmospheric pressure, or sometimes, as in my lab, you might do vacuum, right? So in the absence of any pressure. But gases have a tendency to expand, right, to fill all volume. Right? So to imagine doing an experiment, for example, where we change the pressure, right? So imagine an experiment where I want to measure, for example, like our piston, right? I want to have a constant volume. Sorry, if I wanted to have a constant pressure, right? If I wanted to have a constant pressure while adding heat, right? Adding some heat, then to do that, I really would have had to allow the piston to change side, right? So if I wanted to add heat to a system by raising its temperature, right, and to do a constant pressure experiment, I would have to have the volume change, right? And if dV is greater than 0, then dW was less than 0, right? So in fact, we were doing work by the system, so by doing an expansion. So really, to imagine doing a CP measurement where you're measuring the heat capacity at constant pressure for a gas, it's really a more difficult experiment. So more likely, you're going to measure CV. You're going to measure CV for gases. Okay. So what we're going to do this time is explore this CV, and we're going to have to invoke what we're going to call the Equipartition Theorem. So we'll get to that. All right, so just a reminder, yeah, CV can be defined in terms of U. And once we can measure it, then let me give you some values, right? So these are for gases. So let's do, of course, our favorite gas first. So let's do helium. Let's do CV. Let's do the molar heat capacity, right? So this was CV is 1 over N, partial U, partial T, at constant V. So the units on that are going to be joules per mole K. So for helium, it's 12.5 joules per mole K. For argon, it's 12.5 joules per mole K. For hydrogen, for molecular hydrogen, it's 20.4. For nitrogen, it's 20.8. And for oxygen, it's 21.1. Okay, so you can really see that for monatomic gases, helium, argon, the heat capacity, the CV, the molar heat capacity at constant volume, is very different than for diatomic. This is not dia, it's di, right? Diatomic. 2 atoms. So the question is, can we understand why monatomic gases act like this and diatomic gases have heat capacity like this? Can we understand this from just looking at our heat capacity? Okay, so we said actually last time that just knowing our equation of state, U, cannot tell us, just knowing our equation of state, so for here, our equation of state is going to be PV equals nRT, right? For an ideal gas, even though we know our ideal gas, we don't know U, right? That's not enough information. So we're going to have to actually invoke a theory. And this theory is called the Equipartition Theorem. And you won't find out the microscopic origin, the details of why this works until next semester. Okay? So when you do StatMac, then you'll actually see the origin of this. Okay? So the Equipartition Theorem says partition theorem states that there is 1/2 kBT of energy per degree of freedom. Now, it's worth noting that 1/2 kBT, so if we have, so 1/2 kBT per degree of freedom. Okay, so let's start there. So let's imagine I have a single atom, okay? So I have a single atom of helium. How many degrees of freedom do I have? Okay. So what we mean by degrees of freedom is how many possible motions could I have? So in 3 dimensions, a single helium molecule could move, say, back and forth in x. So let's draw an x, y, z coordinate plane. Right? This helium could also move in y. It could move back and forth. So it could move up and down. Up and down are not different degrees of freedom. They're the same degree of freedom, right? So microscopically in quantum mechanics, you can think of these things as like little oscillators that are existing that have some mode with this frequency, right? Okay, so how many degrees of freedom? There are 3 degrees of freedom. Degrees of freedom, okay? So if we have n atoms, right, then the system will have U, internal degree of freedom, 1/2 n times kBt. Okay, so that'll be the internal energy of the atoms. Okay. Now, it's worth noting that n kb, so the number of atoms times kb, is equivalent to the number of moles times R. Okay. If you're in doubt, work out the units. Okay. So this is joules per mole K. This is joules per mole. So this is joules per K. This is, right? You can see here it's an energy. It's going to have joules per Kelvin times Kelvin. So that's going to be joules. So it's going to be energy. So this is joules per Kelvin. R has units joules per mole Kelvin times moles. So they both have units joules per Kelvin. So that's what they call dimensional analysis. Okay. So you can say that using that, we can say that the internal energy per mole, which we're going to call little u, which is big U over n, can simply be written as 1/2 nRT over n, which is 1/2 RT. Okay? So we're going to have 1/2 RT per mole per degree of freedom. So total internal energy per mole is going to be U is, well, we have 3 degrees of freedom, so we're going to have 3/2 RT. All right. So now, for a monatomic gas, we can calculate for monatomic gas, we can calculate CV, right? So CV is now 1 over n partial big U partial t, constant V, or partial little u partial t, constant V. Okay, that you got really small, but I was trying to make a point. All right. So let's just do it. So now CV is 3/2. So let's just take the 3 and the 3/2 R can come out, right? And you get partial t over partial t, which is just 1. So you get 3/2 R. Isn't that awesome? So we had to invoke the equipartition theorem to get how much internal energy we have per degree of freedom, but now we can see that for a monatomic gas, we can actually work it out. And the units here are joules per mole K. Same as R, right? Okay, so let's go on and look at the diatomic. diatomic gas. So let's imagine we have, for example, we just had N2, right? So we have a nitrogen molecule connected to another nitrogen molecule. So now you can ask yourself, what are the degrees of freedom in this? So you can have motion about the center of mass, right? So let's put ourselves in X, Y, Z coordinate system. Your molecules could also move back and forth around its center of mass and up and down, okay? So in our tally we have degrees of freedom, and we're going to say that we have 3 that are translational, right? 3 that have to do with translating back and forth in space. And so the question is, do we have any other degrees of freedom? Well, our 2 molecules, so you might want to pause it here and sit and think about that question. How many degrees of freedom is this diatomic molecule going to have? I think it's worth pausing and thinking about that for a second. So hopefully you did that. Hopefully you paused and thought about it. Let's see if you came up with the right answer. So you can also imagine that these 2 molecules will rotate in any given plane about this degree of freedom, right? So you can imagine having your molecules rotate like this, or you could imagine having them rotate in this plane, right? So you can see I'm either rotating around X, rotate around the x-axis, right? So this was the x-axis, the y-axis, and the z-axis, basically. So you can either rotate around the x-axis, so this is around x-axis, or you can rotate around the z-axis. So here I'm rotating in the plane. What happens if I rotate along this y-axis? Well, it's like this. So imagine my 2 molecules are kind of like this. So they could move like this, they could move like this, they can move up and down. They can rotate like this around the x-axis. They can rotate like this around the z-axis. But in the y-axis, they're rotating like this. And so there is essentially no moment of inertia in rotation around y-axis. So no energy / degree of freedom. So that one we don't have to count. So in our tally, we have 3 translational and 2 rotational. So our internal degree of freedom, so we're going to have our total U, so for diatomic, our energy, so let's say internal energy per mole, which is going to be little u, is going to be 5/2 RT. And so when we take the derivative, it's going to be just exactly the same. So we're going to get 5/2 partial t partial t. So we're going to get 5/2 r. So little CV is 5/2 R. Again, the units on that one are joules per mole K. Awesome. So now we can already see the basis, right, for the difference in our table between the diatomic molecules and the monatomic molecules in the heat capacity per mole. Okay, let's pause there, and then we will go on and we'll go look back at CP, and we'll start to come up with more relationships between CV and CP.